what have we varied? What have we tried to look at the effects of? We've started with the metal selenide. We've replaced the metal with lead, silver, antimony, indium, a few other things, and looked at operation. How did it affect the way the device worked? And it does. We've changed the active glass layer. We've co-sputtered it with different metals, and that changes operation. We've added carbon. It's a nice germanium analog. How does that change the operation? We've also changed this active layer. So we've used germanium selenide. We also used arsenic selenide, the 50-50 stoichiometry, which has arsenic bonds with similar energy to the germanium selenide that we're using. So the thought was, if this bond theory is correct, perhaps we'll see the same effect with arsenic, 50-50. Germanium telluride, and we've used the sulfide system as well. And then we've also modified active layers around, additional layers around the active layer to change the properties a little bit. And that's where we get into Knowm's device. We've modified quite a few things in the structure to get to something that works well for what they needed. And we've also used copper instead of silver, but copper is really interesting in this system. And it's a completely different situation. I'll talk about that, but you really have to be either subscribed to silver or copper and have a need for the copper in order to use that one. And we fabricated at Boise State all of these devices and looked at their properties. Now I want to make a comment before we move on to those devices. If you actually take this stack with germanium selenide and you use silver on it directly, I want to talk about what happens. I've seen work where I see a normal IV curve with that. My experience is not that. My experience is that when I make this and I deposit silver on top of that germanium selenide, I can take 3 devices next to each other, and this is what I get in terms of IV curves, right next to each other. I could cherry pick this one and say, look at how it works. But reality is, it doesn't work like that. Reality is it has all this stuff going on. And also, this device, it looked okay there, but it only cycled less than 50 times, and it was completely destroyed. So very different. No switching, essentially, in these, and it has no temperature stability. So really, this shows you can't put silver directly on that particular stoichiometry. And I want to talk about why really quick for those materials people here. So if you're actually evaporating, let's say you think you put down a 4060 or Ge2Se3 film, you've evaporated that. What have you done to check that out to make sure? Because I found that this Raman spectrum of the Ge2Se3, very distinct, slight variations in that stoichiometry, for instance, Ge35Se65 or 45 up here, they actually show a different structure, and this structure is significant. We're losing our germanium bonds, we're gaining more different types of germanium selenide bonds. These can photodope, all right? So all of a sudden you have a different type of system. So you may have evaporated your film and think you're putting down 4060 because that was your starting material, but that's not what you have. So if you are seeing something that works and is photodoped without knowing it, you might want to check out the Raman. Raman spectroscopy, if you've got a tool, it's really simple. Deposit it on a wafer and there you go. Just don't put it on a silicon dioxide wafer. Put it on nitride or something like that. All right. So with the metal chalcogenide variation, this is the tin selenide for this particular experiment. And this experiment was done all together, so everything, it's essentially tin selenides of control. Antimony selenide, you start adding that metal and you see different potentials for writing and erasing. Silver selenide, a little bit lower potential. Lead selenide gets very weird. When you first make that device, you see an IV curve that looks like this. Over time, the lead gets into the cell, into the system, and everything switches. The device becomes an on device, and you have to switch it off. It's very interesting chemistry in that one. All right, and then indium selenide. This particular device, this IV curve looks horrible, but the device does cycle okay. Everything looks okay. So even though it looks bad, it actually worked. And if you look at resistance as a function of compliance current, again, for all of these, over all these temperatures, again, silver doesn't migrate through this cell. So you can operate at higher temperatures as long as your materials can, your metal selenides can handle it. Everything looks pretty good. The selenide has that 1 milliamp issue. We don't see that in indium selenide. And we don't really see that here in the lead selenide, which has its own issues. Antimony selenide, we do see it, but the general trend is good operation except for silver selenide at high temperatures. If silver selenide gets heated very high, you start to degrade the device. And silver selenide's a really interesting material in and of itself with all the different phase transitions it has. So who knows, after you deposit it, what you have left on your device. But as you heat it, it starts to lower its resistance until eventually it breaks it. It doesn't really work. So anything with silver selenide I try to avoid, and that includes a photodoped cell because silver selenide is kind of a killer. All right, also right threshold voltages. You can see variation between the forming, which is called the first right here. The device right out of fab always has that forming potential. They all look pretty normal. Once they're formed, they're fairly similar, except for this indium selenide's a little bit weird. But they all look pretty close after forming. So you can see that replacing the metal can have some effect, and what I didn't talk about is cycling, but it can affect things like cycling lifetime. Lead's a good example. It affects how that device operates in the end, how stable is that device, and what kind of pulses can actually program the device. All of that changes with that metal change. So we also tried replacing the selenium with sulfur or tellurium and changed our stacks a little bit. Germanium selenide with a tin sulfide layer, germanium sulfide with a tin sulfide, germanium telluride with a tin selenide. I want to make a note about the germanium sulfide. This may not be a fair test for that one. Notice my stoichiometry is a 4852. It's a bit off from that, 4060. So this may not be a good analog. That was evaporated, so it was hard to control that stoichiometry on that one. But what I did see with that, if it's of any importance, is that the threshold voltage actually shifts all over the place. And this is from device to device and within a device. Once you write the device, you can't predict where it's going to go next. It's just huge. I don't like it one bit. If you just replace it with a tin sulfide over the germanium selenide, no change. No big deal. That sulfide's not doing anything. But the tin is. The tin's doing what it should. Good switching. And if you look at the threshold voltages, the VW1 is the forming, VW2 is the consecutive writing afterwards. And these are DC quasi-static threshold voltages with an integration time, which apparently would matter, probably short integration time for this. You can see that the germanium selenide with the tin sulfide looks pretty good. You can't see the error bars on there. It's plus or minus 1 standard deviation. There wasn't really anything big enough to show up. The sulfide, interestingly, in the very small devices, the 0.13s compared to the 0.25s, they were a bit more stable. So there's something else that may be going on here. Anyway, I don't think that one could necessarily be a fair test. Germanium selenide, tin selenide normal, looks like usual. Germanium telluride has a size dependence, but we've already shown that germanium telluride is a phase change material, especially if you start putting a tin selenide layer on top of it. We've shown that previously. And as a function of compliance current, you get the usual response. So the one thing I can say about our test with the sulfide is we had inconsistent switching voltages, at least in the quarter micron sizes. Some things we don't understand with the size dependence, and I'm not going to pursue that because I don't like the sulfide system, I will say that. The higher threshold voltages are seen in that system as well. And the GE2SE3 device shows really excellent operating characteristics compared to those other materials, so we're sticking with that one and modifying things around it because it seems to work so well. We've taken the active layer and we've co-sputtered it with some metals as well as with carbon to investigate how changing the germanium bond structure with these metals in situ will change the response and how the devices work. And the carbon devices, just as a quick comment, because I don't present any data for these in this talk, they were really interesting. I liked them quite a bit. What they did was they They switched. They liked very low current. They were clean switching devices. And by low current, they like, you want a compliance current of 100 nanoamps on those. Otherwise, it tends to cause the device to get into a low resistance state and not want to leave. And the operation, it was hard to find anything when switching with a quasi-static system, hard to find anything that wasn't binary. I'm sure it's there. We didn't pulse it very well to see, but it was an interesting system. And the tungsten, tin, and chromium, our goal was to see if we could change the resistances that we could write to make it better analog resistance programming, alter the resistance ranges a little bit. Let's say we don't want to operate at something which is high power, we want higher resistances, 100K. We thought this might be a way to get there. And tungsten, when it's with germanium selenide, has a tendency to want to operate both as a phase change device and an ion conducting device. So we were hoping we could use both properties with that system. And I want to point out the Raman spectrum again for the materials folks. When you add chromium to germanium selenide, this is 1 atomic percent. You don't change that spectrum. It's not going into those germanium-germanium bonds. Same with tin. And we know that from theoretical calculations, the tin goes in interstitial until you add electrons to that system, and then it will bond. Tungsten, on the other hand, gets in there, and you can recognize the crystalline peaks, so it wants to start to crystallize. So again, Raman's a really handy tool if you can look at your films with it.